Leeward Community College has a beautiful view of Pearl Harbor. I'm standing on the balcony here at the college, and in the background you can see several decommissioned military ships that are slowly being stripped for their parts. We call that the ship graveyard here at the college. Those ships are reminiscent of a time not forgotten, especially for some of the old-timers here on the island of Oahu, because on December 7th, 1941, Japanese airplanes invaded this island, and those same beautiful waters were then a fiery inferno. On that day, order was broken in our country. And for those old-timers, that day is remembered. For me, today, the view is a serene one. And I often come out to this balcony to talk on the phone with my family back in Virginia, or to read my Bible. Sometimes I may even come out here to escape students who are knocking at my office door in order to prepare for the next class lecture. In today's lecture, we focus on the established order of solids in their crystalline form. And I think you'll find this lecture quite interesting today. Crystals can be beautiful objects to perceive, and their structure oftentimes contains many interesting geometrical features. And looking at a crystal can be a quite captivating experience. But to the scientific mind, it's no surprise that this outward expression of beauty and geometry is a reflection of the internal ordering that's occurring among the particles that form the crystal. I'm holding here a piece of quartz crystal that was lent to me by Roger Kwok, who's a professor of science here at Leeward Community College. Roger also lent several other crystals for this lecture that I'll show you here in just a moment. Today we delve into the realm of solids in their crystalline form, which is the most naturally occurring form for a solid to be in. Some solids are amorphous, meaning their structure has no order. The particles are frozen in whatever configuration they happen to be in at the time the solid forms. Glass is an example where the particles that form the glass have no order in them. However, most solids are crystalline in nature, meaning the particles that form the solid have a certain ordering that exists among them. And today we will study crystals by looking at that order, by focusing in on what is the arrangement of particles that form the crystal or form the solid. So to start off, let's first define what a crystal is and see how one is formed. A solid is crystalline when the particles it is composed of possess a certain internal order called the crystal lattice. Crystals form over time when the forces of interaction cause the particles to align properly. Conditions need to be just right, and they have to exist for a long period of time. And when you have conditions that remain constant for a long period of time, the pressure and the temperature remain relatively constant, then the forces of interaction that exist between the particles are also remaining relatively constant. And given enough time, the forces will guide the particles right into place perfectly. And that keeps on happening basically off into infinity or until the crystal runs out of room. So given enough time, the right conditions, and the right types of particles, a crystal will basically form. So there are lots of situations where conditions remain constant over long periods of time with the right types of particles, and that can occur deep within caverns in the earth and so on. So because there are many types of conditions out there that are constant and many types of particles as well, you will find lots of different types of crystals that form in nature. One way to classify crystals is by the particles from which it is composed. And many crystals are composed of atoms. There are copper crystals out there, and I do have a piece of copper crystal that I'll show you here up close. Now, the structure of this copper crystal is not as geometrical as the quartz crystal that I showed you a moment ago, but this is crystalline nonetheless. The particles do have a certain order among them that you would see if you were to break out your atomic level magnifying glass. Silver and gold also come in crystalline form. Now, this gold wedding ring, which symbolizes the covenant that I made with my beautiful wife Alicia, is actually not crystalline gold. This gold has been heated up and cooled down many times over, and that ordering in the particles, that crystal lattice, has long since been removed. But if you were to go out into a cave somewhere and discover a piece of gold up there in the wall of the cave, not only would you be quite lucky, but you would see gold in its crystalline form, and you would see that jaggedness on the surface of the gold. Many crystals are formed from molecules, and you've no doubt seen water in its crystalline form because that's ice. You've probably seen carbon dioxide in its crystalline form, which is dry ice. In fact, in our previous lecture, we discussed some differences between water and carbon dioxide with the help of phase diagrams. Silicon dioxide, which is that quartz crystal that I showed you. I'll show you that one again a little bit more closely. Beautiful geometric features in the quartz. So here's another piece of quartz, a little bit smaller. You've also probably seen C12H22O11 because that's sucrose, or table sugar. And when you were a kid, you may have even made rock candy, which is a very large sucrose crystal. Sulfur comes in a molecular form as S8 molecules, 8 sulfur atoms attached together in the shape of a ring. And these ring-shaped molecules are the particles that form the crystal. I do have a piece of sulfur crystal here. You can find sulfur crystals near volcanoes. Beautiful yellow crystal. You can probably see some of the geometric features in the sulfur crystal. Many crystals are composed of ions, and you've also probably seen sodium chloride, which is table salt, but in the crystal community it's known as halite. You may have seen calcium carbonate, which is calcite. Calcite forms these really nice crystals, and I'll show you a piece of calcite right here. An almost perfect piece of calcite, where the edges or the faces are almost perfect parallelograms. Now, this piece of calcite was actually cleaved, meaning it came from a larger rock, and that rock was struck with a hammer or something, and this is the piece that came off. So very interesting how you can strike a rock and have something like this break off. Calcium fluoride, or fluorite, forms these nice green crystals, and I'll show you a piece of fluorite. If you look closely, you might be able to see some box-shaped portions of this crystal. It's like a bunch of boxes that are stuck together. Really nice looking green crystal. And my favorite up here is iron sulfide, or pyrite. Pyrite forms these nice cubical shaped crystals. Very metallic looking. An almost perfect cube of pyrite here. Now, pyrite is also known as fool's gold, and whereas this is a more perfect piece of pyrite, it probably had a lot of time to form, and that's why it formed so perfectly. If you see a less perfect piece of pyrite, it might look like this, and maybe you can see some of those cubes kind of stuck together. So this is known as fool's gold, and if you were to see a piece like this on the wall of a cave, you might mistakenly thought you struck it rich. So there are many different types of crystals out there. Some of them are quite beautiful. They contain certain features in common, and the most common feature is that the particles have a certain order among them called the crystal lattice. Now, the various crystals contain different crystal lattices, but by studying one particular type of crystal lattice, we'll be able to understand something about all of them. And I've drawn here a representative lattice for you to see. What the lattice is an arrangement of particles in three-dimensional space, and it's a repeating pattern of units. So here is a lattice which shows a repeating pattern that occurs over and over and over again, basically off into three-dimensional space. And the unit that's being repeated here is the shape of a box or a cube. So I've drawn here actually 27 cubes stacked, 3 cubes tall, 3 cubes wide, and 3 cubes thick. And I've taken one out, kind of zoomed it up for you to get a better look at it. You can see the particle at each of the 8 corners of the cube. Now, many crystals do take on the cubic lattice and have a smallest repeating unit or unit cell, which is in the shape of a cube. It might not be a big surprise that that piece of pyrite here is formed from that cubic lattice. And if you were to break out your atomic level magnifying glass, you would see the particles in the shape of a cube, or basically arranged in a cubic form, which is repeated over and over and over again. Now, it might be more of a surprise, but that copper is also formed from the cubic lattice. Not as obvious here as it is right here. So sometimes the large shape of the crystal reflects exactly the small shape of the unit cell from which the crystal is composed of, but other times it's not as obvious. Another crystal that is formed from the cubic lattice is that piece of fluorite right here. So you can probably see some of the cubic features in the fluorite. The sulfur that I showed you is formed from a closely related type of lattice, which is composed of these box-shaped unit cells stacked over and over and over again. So a little bit closely related to the cube, but not quite a perfect cube. The piece of calcite that I showed you right here, it's very interesting that that calcite is formed from a lattice that is composed of this shape, which is called the rhomb. So it's almost an identical shape. It actually is identical to the large shape of the crystal. This rhomb right here is the same unit cell from which quartz is composed of, but not as obvious here as it is for the fluorite. So all crystals have their own crystal lattice, which is composed from a certain unit cell. And the way we're going to study crystals is by focusing on one type of lattice and one type of unit cell, which is the simplest type, also probably the most interesting type, which is the cubic unit cell. So before we do that, let's first take a look at how crystals are studied, how this crystal lattice is observed, and that's by X-ray crystallography. The structure of a crystal lattice can be found by X-ray crystallography. In this method, passing an X-ray beam through a crystal creates an interference pattern on the other side of the crystal, and this interference pattern is based on the particle positions within the crystal. So to see how this method works and to understand what an interference pattern is, let's first examine the interference pattern for ocean waves that are hitting the shore. Suppose you have a set of ocean waves that are traveling towards shore and they hit some wall that has a couple of holes in the wall that are separated by some distance. And further, suppose that the separation of the holes is comparable in size to the wavelength of the waves that are hitting the shore. Now what happens is at each hole, another wave is emanated on the other side of the hole in a circular fashion. And this is a well-known phenomenon, and you can see this happen all the time if you study ocean waves. So if you have a circular wave emanating from this hole and another one from that hole at the same time, then these two circular waves will interact with each other at certain locations in the water, and they'll kind of double up and create a really tall wave. That's called constructive interference. Well, at other locations in the water, the waves will sort of cancel off and the water will be flat, and that's called destructive interference. So if you observe the situation from some further location, you will see that interference pattern where the waves will constructively interfere and destructively interfere. And that interference pattern can be studied and used to predict the separation of the two holes from where the waves first emanated from. So just by looking at the interference pattern, you can predict how far the holes were separated from one another. Well, that's exactly what is done in X-ray crystallography. In X-ray crystallography, you have a source of X-rays which are really high energy light waves, and the wavelength of X-rays are comparable to the size of an atom or a molecule or particle within a crystal. So what you do is you shoot a beam of X-rays, which are a bunch of light waves traveling at the same time, and you pass that through a crystal. And these X-ray waves interact with the particles in the crystal and are then deflected. And on the other side of the crystal, all of those deflected X-rays will interact with each other and will also generate an interference pattern. And you call this a diffraction pattern. And that diffraction pattern can be collected and studied and used to determine the positions of the particles that are in the crystal. And many crystals have been studied by X-ray crystallography, and many crystal lattices have been solved. And so those crystal lattices being built up by their small unit cell, we have found many types of unit cells that occur within the different crystal lattices out there. And so I've drawn several examples of unit cells. Here is a cubic unit cell where all of the edge lengths are equal and it's all right angles. So many particles are found to take on the cubic arrangement in crystals. Other crystals have their particles arranged in a sort of elongated box called the orthorhomb. Another boxy type of unit shell is the tetragonal arrangement. But there are various unit cells that are not boxy in shape, One example is the rhombohedral arrangement, which actually is the same arrangement as that piece of cleaved calcite that I showed you in the previous slide. So in this lecture, we'll focus on one type of lattice, the one that's built up from the cubic unit cell. In the cubic lattice system, particle arrangement can be divided into three main classes: primitive, also known as simple, face-centered, and body-centered. In this discussion, the particles that we're working with are atoms. It's much easier to deal with atoms versus molecules because an atom is a spherical object. The primitive or simple cubic lattice is taken on by the element polonium, and this lattice is represented right here in this two-dimensional rendition where the particles are circles. And you can see the particles are lined up perfectly. This line right here is exactly lined up with that line and the following line, and you can imagine this going off into all directions. The three-dimensional system will have particles coming out of the board and particles going back into the board as well. But you can get a good understanding of this system by looking at the two-dimensional lattice. Now, one thing you might notice is that these particles in this line are not packed in very well with the particles in the adjoining lines. They're not fitting into the crevices of the next line over. So it's not very efficient way to pack particles. And you would describe that by the packing efficiency. The packing efficiency of the primitive lattice is only 52%. So in the three-dimensional space occupied by a primitive crystal lattice, only 52% of that space is actually occupied by particles. The other 48% is empty space, which is the crevices between the particles. Now, the coordination number in this lattice is 6. And what the coordination number is how many other particles each one is in contact with. So if you look at, say, this particle right here, and you ask, how many other particles is it in contact with? Well, in this single two-dimensional layer, you can count 4 other particles. But in 3 dimensions, there's going to be one more particle coming out of the board that it's in contact with, and one more particle going back into the board. So this particle is actually in contact with 6 other particles. Coordination number 6. And since every particle has an identical environment, the coordination number is 6 for all of the particles. So it's a property of the lattice in general. Now, this lattice can be divided up into individual repeating unit cells. And one way to draw the unit cell is as follows. The unit cells in this two-dimensional lattice are represented as squares, and you can see that the square starts from the beginning of this particle and it goes over to the middle of that particle. So this square can be repeated over and over and over again, and all of the squares look the exact same, so this is a valid unit cell. Now, to get a better understanding of the three-dimensional unit cell, I've popped this one out into 3 dimensions for you, and you can see the front face of this 3-dimensional cubic unit cell looks the exact same as that 2-dimensional one, where the face goes right through the middle of these front 4 particles. Now, in the 3-dimensional unit cell, you have another set of 4 particles behind these front 4 particles. And so there's actually 8 particles that are in contact with this single unit cell. Now you might ask, inside this unit cell, how many particles are there? Well, the answer is there's the equivalent of one particle. Now that might be kind of difficult to see because you don't see an entire particle inside this box. What you see are 8 pieces of a particle inside the box. And so what do those pieces add up to? Well, the answer is they add up to the equivalent of one particle. And to better see that, I've drawn 4 unit cells here where a particle has been immersed into those 4 unit cells. So 1/2 of this blue particle is immersed into those 4 unit cells, and the other half of the blue particle is immersed into the upper 4 unit cells that are not drawn. So if this particle is sitting right at the corner of these 4 lower unit cells, then what fraction of the particle is inside this cell right here? Well, the answer is 1/8 of the particle. Anytime you have a particle that's centered at a corner, 1/8 of the particle is inside the box, and the other 7/8 of the particle are in the other 7 adjoining unit cells. So here, where you have this particle that's sitting centered right at this corner, 1/8 of the particle is actually inside this box, and the other 7/8 are in the other 7 unit cells that are in contact at that corner. And so this corner, 1/8 of the particle is inside the box, and the other corners also have 1/8 of the particle inside the same box. So since there are 8 corners, you can count them all up. 8/8 means the equivalent of one particle completely inside this unit cell. Now, you could ask, how long is this edge length, L, of the unit cell? Well, it's pretty simple to determine that for the primitive system. You can see that the edge length is twice the radius, because going from this corner, which is at the center of this particle, over to that corner, which is at the center of the next particle, you pass through 2 radii. So the edge length is 2r here. Now, the simple or primitive system is a kind of a weak lattice because there's not a lot of particle-particle contact here. The efficiency is pretty low, and so because there's not a lot of particle-particle contact, the coordination number is only 6, it's a pretty easy lattice to break up. Other crystal lattices have a higher coordination number and more particle-particle contact and are therefore stronger. If you take a look at the face-centered lattice, this is actually the most efficient way to pack particles. And the face-centered lattice is taken on by several elements, gold and aluminum included. I've drawn here 3 layers of the face-centered lattice. The pink particles are in the back, the yellow particles are in the middle, and the blue particles are furthest out of the board. Now these particles are all of the same type, they're just color-coded to help us see which ones are which. So I think you'll get the best understanding by focusing on the yellow particles that are in the middle layer. Now, there are also 16 yellow particles drawn here, just like there are 16 particles drawn over there. But these yellow particles, whereas they're all lined up right here, these 4 particles are fitting into the crevices of the particles in the next line, which are fitting into the crevices of the particles in the next line. And so the lines are sort of staggered, and these yellow particles cannot be packed together any more tightly than they are. So this yellow layer is the most efficient way to pack those yellow particles. And similarly, the pink particles in the layer behind that are also packed in the most efficient manner as well. Identical staggering in the pink particles. And the blue particles as well. I've only drawn a few blue particles. If you wanted to add more blue particles in this outer layer, you would put one right here over this hole that is formed between the yellow particles and the pink particles behind it. Put one right over that hole, one over this hole, this one, and that one. So these blue particles are placed over the holes that are formed between the yellow and the pink particles behind the yellow ones. Now there's actually another way that the blue particles can be placed on top of the yellow layer. And instead of putting them over the holes, they could have been placed over the pink particles, directly on top of the pink particles. So the blue particles could have placed, instead of right here, it could have been placed here, here, and here. And then again, right there, there, and there. Now that would have also been an efficient way to pack the blue particles together right on top of the yellow particles. But if you did that, the blue particles would be lined up perfectly with all of the pink particles, and you wouldn't be able to see the pink particles behind that. And that type of lattice is actually not a cubic lattice. There is no way to draw a cubic unit cell with that arrangement. Even though it's also a very close way to pack particles, it's a different type of lattice. This type of lattice is a cubic arrangement, and in order to see the actual cubic unit cell, which is rather difficult, I've done my best here. Now this cubic unit cell has been color-coded as well, and you can see this blue particle has been drawn right there. These 6 yellow particles along the white triangle are drawn right here. 1, 2, 3, 4, 5, 6. And then the pink particles, this one, and that one, are actually this, this, and that one right there. Now, the face-centered unit cell is somewhat different than the primitive unit cell. You still have a particle at each of the 8 corners. But in addition to that, you also have a particle located at each of the 6 faces. Now, when a particle is at a face, one half of the particle is inside the box, and the other half is outside the box. And you can see that by looking at this little drawing that shows a particle sitting right on a face, centered on a face. Half of it is inside this unit cell, and half of it is in the other unit cell that's not drawn. Now, how many atoms are inside this face-centered unit cell? Well, the answer is 4, and the way you can determine that is by looking at the 8 corners. 8 corners, and at each corner 1/8 of the particle is inside the box, so that is 1 particle inside the box. But then you have 6 faces, and at each face you have 1/2 of the particle in the box. So that's 6 halves as well. So 8/8 and 6 halves add up to the equivalent of 4 particles inside this unit cell. Now, the packing efficiency for the face-centered lattice is a lot greater than the primitive lattice. This is the maximum packing efficiency for packing particles, and it's 74%. So there's a lot of particle-particle contact here, and the coordination number is actually 12. So you remember what the coordination number is. It's how many other particles each one is in contact with. So one way to see the coordination number is to look at maybe one of these yellow particles, and you can see that this yellow particle is touching 6 other yellow particles in the same layer. So how many particles is it touching in the layer behind it? Well, it's touching the other 3 pink particles in the layer behind it, and then in the layer in front of it, it would be touching 3 blue particles. So the coordination number of this one is 12, and you could see that each yellow particle will be touching 3 blue particles in the layer in front. So a coordination number of 12 means a lot of particle-particle contact, so this is a rather strong lattice. Now, the edge length of the face-centered crystal lattice is a little more complicated to get to than the primitive lattice. The length of the edge of this box is actually 2 times root 2 times the atomic radius. So it's no longer twice the radius because there's a space between these 2 corner particles. So it's more than twice the radius. And the way you can find the edge length is to draw a triangle from one corner all the way to the other corner and then back. So if you look at this triangle right here, this is the edge length L, that is the edge length L, and the length of the diagonal is 4 times the radius. It's going right through these atoms, so it's 4 times the radius. So I've taken this triangle and I've put it right there. So you have an edge length, the same edge length, and then 4 times the radius. And because this is a right triangle, you can use the Pythagorean theorem to solve for L. And when you solve for L, it turns out that L is 2 times root 2 times R. So the last type of cubic unit cell or cubic arrangement is the bodied center cubic, which is taken on by elements molybdenum and barium. And the bodied center arrangement is more obviously a cubic arrangement as opposed to the face-centered arrangement. The bodied center arrangement, we can see that the particles sort of line up in squares. Now what you have here in the bodied center arrangement is you have one layer staggered relative to the other layer, and so the staggering kind of alternates back and forth. You can imagine these white particles that are in the layer behind, there would be another equivalent layer directly in front of these clear particles that would kind of line up with the white particles. So the packing efficiency in the bodied center cubic is 68%, which is in the middle of the primitive and face-centered. The coordination number for bodied center arrangement is 8. And this is rather easy to see, I think, because if you look at any one particle, say this white one right here, it's in contact with these 4 clear particles in front and another 4 particles in the equivalent layer behind it. So a coordination number of 8 for all of the particles. Now, I've drawn here several unit cells represented by squares, and if we pop one out, you can see the 4 clear particles right here, and then the white particle behind it, and then the other 4 clear particles are behind that. So again, in this unit cell, you have a particle at each of the 8 corners, but now you have one completely inside the box. So if you add up all of those portions of particles as well as the one inside the box, you get the equivalent of 2 particles inside this unit cell. So the edge length of the bodied center unit cell is more complicated than the face-centered. The edge length turns out to be 4 times the radius over the square root of 3. Now, rather than show you the derivation, I think it's a good exercise if you go ahead and derive this yourself. So in order to do that, you want to find the triangle that needs to be drawn, and again, you'll use the Pythagorean theorem. But what triangle are you going to use? It's not the same one that you would use for the face-centered lattice. So try to find that triangle and go ahead and derive this formula for the edge length in terms of the atomic radius. The groundwork that we've just laid out on the cubic crystal lattices will allow us to predict certain properties of substances which crystallize in those lattices. And the properties that we'll be examining are the intensive properties, meaning they do not depend on how much material. So for an intensive property, it's the same whether you have this much material or that much. An example is the density. So the density of a substance doesn't depend on how much material. The density is the same as if it's that much versus that much, or versus even a tiny unit cell's worth of material. And that's the approach that we'll be taking, is to focus in on just a unit cell. And the property of that unit cell will be the same as the property of the large material in general. So the first example asks us to find the fraction of empty space in the bodied centered cubic lattice. Now, the fraction of empty space is closely related to the packing efficiency. You remember the packing efficiency, which is 68% for the bodied centered lattice, is the percentage of filled space within the lattice. Now, if the percentage of filled space in the bodied center cubic lattice is 68%, then the percentage of empty space in the bodied center cubic lattice would be 32%. So if you convert that percentage of empty space to fraction of empty space, we should expect about 0.32 for the fraction of empty space. So let's see what we get. We can calculate the fraction of empty space as 1 minus the fraction of filled space. The fractions add up to 1. So if you take 1 minus the fraction of filled space, and the fraction of filled space would be the volume of the atoms inside the unit cell divided by the volume of the unit cell. So that's the fraction of filled space in the unit cell. So 1 minus the fraction of filled space would be the fraction of empty space. Now we can rewrite this fraction. 1 minus the volume of the atoms would be the volume of one atom, which is 4/3 times pi r cubed, where r is the atomic radius, times 2, because there are 2 atoms in the BCC unit cell. So the volume of the atoms in the BCC unit cell divided by the entire volume of the cell, which is the edge length cubed. And you remember for the bodied center cubic unit cell, the edge length is 4r over square root of 3. So this right here is the expression, and if you reduce it on down, there will be a lot of cancellation occur. The r cubes will cancel off, and some other stuff will cancel off as well. You'll be left with 1 minus square root of 3 times pi divided by 8. So if you calculate this, it's 1 minus 0.68, which is where that 68% comes from, and a bunch more decimal places. And so you end up with 0.319825238 So you can continue this on if you prefer, because all of these digits are significant. That's because all of these numbers that you use to calculate it are exact numbers. So quite a lot of significant figures, as many as you need. The next example, gold crystallizes in the face-centered cubic arrangement or lattice and has an atomic radius of 1.44 angstroms. Find the density. So density is another intensive property. Now, we'll just calculate the density of the unit cell, and that will be the same as the density of gold. So the density of the unit cell will be the mass inside the unit cell divided by the volume of the unit cell. So the mass inside the unit cell will be the mass of 4 atoms, because there are 4 atoms inside a face-centered cubic unit cell. So the way you calculate the mass of 4 atoms is as follows. We know for gold the atomic mass is 196.97 grams per mole. So you can convert this to grams per atom by the following conversion factor. 1 mole is Avogadro's number of atoms. So the moles cancel off and you'll be left with grams per atom. And then when you multiply it by 4 atoms, you get grams up here in the top. So that's how many total grams are in 1 unit cell. And you divide by the volume. For the face center cubic unit cell, the volume of the cell is the edge length cubed, which is 2 times root 2 times r, all cubed. And if you plug that in, 2 times root 2 times the atomic radius, 1.44 angstroms. Now, we'll convert that atomic radius to centimeters. 100 centimeters is the same as 10 to the 10 power angstroms. So the angstroms cancels, and then you have 2 times the square root of 2 times the atomic radius in centimeters, all cubed. And if you do this calculation, you get 19.3346 grams per centimeter cubed, but it's a 3 sig fig number because of the atomic radius, and so it's 19.3 grams per centimeter cubed. Now, if you want to compare this to the density of water, which is 1 gram per centimeter cubed, you can see that this is more than 19 times heavier than water. Gold's quite heavy. The last example, polonium crystallizes in the primitive lattice and has a density of 9.196 grams per centimeter cubed. Find the atomic radius of polonium. Now, the equation that we'll be using is very similar to the previous equation in example 2, because we're given the density and asked to find the radius here, whereas in the previous example we were given the radius and asked to find the density. So the equation will be very similar, we'll just be working backwards. And if you want to compare the two, you'll notice very few differences. The only differences are in the value for the density. This is unknown, and we know the density here. The atomic mass for polonium is 209 grams per mole. And there's only 1 atom in the unit cell of the primitive lattice. And in the denominator, the volume is the edge length cubed, but the edge length for the primitive lattice is 2 times the radius. So here, the radius is the unknown, and with the same conversion factor, if we solve for the radius, we'll get the answer in angstroms. So doing that, we calculate 1.20 angstroms for polonium, which is close to the known value. So it's very interesting how we can calculate these intensive properties, or use the intensive properties to calculate certain atomic properties with just a knowledge of the crystal lattice. I hope you have enjoyed this lecture. I have really enjoyed putting it together. And this does close up the first phase of our course on phases of matter. In the next portion of our course, we'll start to cover solutions. So in the next several lectures, we'll get into various aspects of solutions. So I hope you join me for that. Aloha.